Let me check. Okay, yes, we're live. I think some of you saw my premiere coming out tonight and thought that you missed my live, but indeed that was a premiere of a video and a clip, and the live is here. This is the live right now, right here, right now. So please do come on over and join us. Indeed, here it is right here. So again, good morning, good afternoon, good evening, good night, good midday, good mid-evening to everybody, indeed, all of the continents, all of the Africa, all of Asia, all of Europe, all of Antarctica, Australia, New Zealand, North and South America. Thank you so much for liking the live. Could you please say something in the chat? Could you please maybe share the live, give a super chat? I don't know, all those types of good things. Nathan says, I was almost asleep. I missed you. Hello, Nathan. Hello, Nathan. Oh my goodness. You have to definitely, we have a lot of catching up to do. Yes, indeed. We have a lot of catching up to do because we have been missing each other a lot. Hello, Ray, with the cyst. Hello. Good evening, gentlemen and ladies and children. Please do like the live. Can we get 20 likes? Can we get 20,000 likes? Can we get a super chat? Can we get $500? Can we get $500,000? All of those, anything in that ballpark would be most amazing. So Nathan, I saw your kayaking pictures on your shorts videos. Thank you so much for sharing. Thank you so much for liking the live. So today I was gonna take the day off and do mainly my self-care routines, but I did sort of a longer gym. Then I came back, then I ate, and here I am. Now I'm here. I was gonna do laundry again, more laundry, but instead, I'm catching up on some of my lives this week because I'll actually take a little bit of a break, possibly next week. So next week I will still go live a lot, but there might be a couple of days that I have to take off next week. So here we are. Good evening. Good evening. So yesterday and the day before, we've been talking about time travel from the book A Brief History of Time by Stephen Hawking, and we've been looking at all these different sort of possibilities when it comes to time travel and what it all means, and what sorts of things one could make a time machine out of, as well as what pairs of particles may or may not do, particle antiparticle shenanigans, and things like that. So we've been kind of doing all of that recently. Hello, everybody. Welcome to the live. Can we please get 20 likes? That would be amazing. I did see tour laundry video. I had a similar washer in my old apartment. Oh God, oh, thank you so much for watching my laundry video. Thank you so much. If you could please like the live, that would be great. Everybody who's joining, and feel free to say something in the chat. I usually hang out and give people shout outs in the beginning of the lives, and say hi to everybody, and I can read out your username and go from there. Hello. Vitim says hi. Hello, Vit M or Vit I M. Dora Madness says, ladies and gents, we need 20 likes immediately. Please do urgently give us 20 likes. That would be most amazing. Clint Wright says hello. Hello, Clint. Hi, Doro. Thank you for that most amazing message that I have now pinned. Ladies and gents, please do give us some likes. Hello, Clint. Hello, vitamins / vitim / vit I am. Welcome. I liked and subbed. Thank you so much. So yesterday we were talking about who is coming from where. And if you don't mind, you could share in the chat where you are joining from. You don't have to give us a lot of details, but some people were sharing their continents and countries, such as Africa, welcome, Iran, welcome, Belgium, welcome, North America, welcome, Mexico, welcome, oh my gosh, Texas, welcome, California, welcome, Europe, welcome, Australia, welcome, Indiana. Oh, I didn't realize you're in Indiana, Nathan. Oh my goodness, I was pretty close to Indiana. For a while there, I lived in Ohio. So I was your neighbor. That is a classic troll name. Yeah, Doris. So Ray is our new friend. I think this is Ray's. I just say the first word, the first one, Ray. This is his or hers, probably his first, no, second night in a row on the live. Cypher says Memphis, Tennessee. Wow, Memphis. Ike says I'm your biggest fan. Thank you so much, Ike. Hello, IKE with the 3 exclamations. Love it. Thank you so much for liking the live. Oh my gosh. Thank you. Thank you. Thank you. Thank you. Thank you so much for liking the live and for being here and for joining. Welcome indeed. Cypher says Memphis. Oh my gosh. Welcome Tennessee. Nathan says what's so close yet so far away? Yes, I was very close to Indiana. Clint says tomorrow's my birthday. Happy birthday to you. Happy birthday to you. Happy birthday, Clint. Tomorrow, as in, is it going to be soon? Like in 8 minutes? It's going to be 11:52 here. So is it going to be in 8 minutes? Is your birthday? Are you on the East Coast? Clint, my friend. Grimmy says, I'm here to leave a like, then I'm going to bed. Good night. Good night, Grimace. Oh, thank you. You made my day. Of course, I'm not done singing. I love birthdays. I just love it. I love birthdays. It's the main thing I celebrate in my family and myself. Clint says it's 10:54. Oh, it's your central time. Got it. Thank you so much, everybody, for liking the live. Please do give us some more likes. That would be amazing. Can we get 10 likes? Can we get 20 likes? Thank you so much. Grimmy says, see you in 5. What does that even mean? Are you going to go to bed together or are you playing video games instead of being in class here? Because we're going to be talking about physics soon here, guys. If you didn't know, in case you're new here. Sometimes I don't like to announce it in the beginning because then everybody leaves. But that is before they find out that they actually love this stuff and they want to stay. It's my birthday too. Happy birthday to you. It's your birthday too, really? What day is it tomorrow? Actually, there is a lot of people being born in May constantly. That is true. A lot of my friends I saw on Facebook actually are a May baby. What? A bunch of Tauruses? A bunch of Taurans? Happy birthday. No. Happy birthday to you. Happy birthday. It's not your birthday? Grimmy says, we'll be back in 5, but we definitely share a bed. Okay. That's okay. Okay. Steven! Clint says you're kind. You are kind? Okay. Thank you. Thank you, Clint. And happy birthday tomorrow. It's my second birthday this year. Happy birthday to Ray. Happy birthday. So, Ray, did you already have a birthday? Which month was it? January, February, March, April. Which month was it? Are you an Aries? Are you a warrior? Ray says my favorite Twitter account is a guy named Racist Man. Oh, you made me read that. Oh my God. August. August is that Leo or Virgo? Steven says, Dora, you got pages to upload. And of course, Steven Spears. Ray is a classic troll. Clint says, now that's rude. Leo. What's rude? The username you mean, right? I didn't do that on purpose. YouTube, don't YouTube? You know, I don't want to get in trouble with YouTube. We've said worse though, but I try not to say anything worse. Okay, also, Can we get 10 likes and can we get 20 likes? Okay, so today we will talk about unification of physics, which is, by the way, a pretty difficult topic as far as the work on actually the topic, goes in, as in it's very difficult to do unification is what I'm trying to spit out. But we have talked about unification quite a bit on this channel. So some of this will be kind of like review. It won't be totally new to you or something you've never heard of if you've been kind of coming to these likes, and by likes I mean lives, and I read the word likes. If you've been coming to these likes, the username, we don't need 10, we need 20. We first need 10 and then we need 20 likes. Yes, you need 100 likes. Thank you, Clint. Could you please share this live with your entire family, friends, and neighbors and colleagues so that we can get 20,000 likes? You deserve 100,000 likes and subs. Thank you so much. We need 20. Clint is about to be... What do you mean? Don't you ban Clint, the one good guy here. Okay, so now I will say that unification is something that we have mentioned quite a bit. And by unification, I mean really a theory of everything. And also, remember, we were talking about this, that you would really need to kind of unify gravitation with quantum mechanics. Now, even though general relativity and quantum mechanics have not seen eye to eye historically, and indeed there are sort of differences between them that are still unresolved, and general relativity is more of a classical theory. It is not classical mechanics as in Newtonian mechanics, as an update to Newtonian mechanics or classical mechanics as presented by Newton. It brings in the relativity, obviously, like that's why it's called general relativity, and it's an updated theory for gravitation on top of what we kind of already knew with Newtonian mechanics. If you want further accuracy, if you want further corrections to that, you would use general theory of relativity. But then parallel to that, what kind of developed in the 20th century and what also kind of took off a lot, and even though considered bizarre, uncertain, and probabilistic, what really took off in the 20th century of physics is quantum mechanics. And even though there were many people, even some of the founders of quantum mechanics, who didn't really like quantum mechanics and what it was implying, some of the bizarreness of it, it actually stands the test of time, and it actually is a very successful theory because it's been experimentally shown, and it has great experimental success, and it has led to, of course, particle physics, the standard model of particle physics, and even beyond standard model particle physics. So quantum mechanics, whether you like it or not, you can love it, hate it, can't ignore it, is one of those things that is not a classical theory, of course. Classical means deterministic. Quantum means probabilistic. Classical means large scales. Quantum means small scales. Classical means Newton, Einstein. Quantum means Niels Bohr and many others. Schrödinger, as well. Schrödinger's cat, that whole thing, that whole story has to do with quantum mechanics. Schrödinger himself actually did not like the probabilistic nature of quantum mechanics, though. Dirac, another great guy for quantum mechanics. So Schrödinger, Dirac, Niels Bohr, these are the people, right? But it's funny because Einstein was actually a contributor to the old quantum mechanics, as in he gave us the dual nature of light, where light has a wave particle nature, and he gave us the photoelectric effect along with other people, I'm sure, that also contributed. And the thing is that the old quantum mechanics was sort of limited to light having a dual nature with both wave and particle nature. But then it really sort of took off, and matter started to have waves. And when you write down equations for motion of things that are at the scale of quantum scales or small scales or microscopic scales or subatomic scales. These are all sort of synonyms of the same thing that I'm trying to say, small things, subatomic scales. Then turns out when you try to do the mechanics of that, which is to say maybe the position of that thing, little thing, say an electron, as a function of time, what happens is that you cannot really deterministically determine where this thing is. It is a probabilistic wave. It's given by a wave equation, and the wave equation actually gives you the probability of finding that thing, not the deterministic answer for finding that thing. Stuff like that. And uncertainty is an intrinsic part of this mechanics, and so we call this quantum mechanics, quantum physics, same thing. And it's led to, of course, also particle physics, and one of the contributors to that is Feynman, and we were kind of talking about the Feynman diagrams last night, where we basically established that, you know, even the wormholes and time travel as a topic can sound a little bit like sci-fi, science fiction, and it's very popular in science fiction. And it's very much written about. I mean, we've got people in the chat who's writing science fiction books, actually, like Steven. So it's very popular to think about wormholes and time travel, but it actually is quite real as well. It is allowed in physics to be able to do time travel. It's just not very pragmatic. It's just not very realistic to have those conditions be achieved technologically at this point. But we talked about the physics of it and how it is kind of possible, and especially it may just be very possible at the microscopic level. We talked about how particles and antiparticles are kind of actually already doing time travel. Okay, so maybe not a macroscopic level like you and I, bigger objects, maybe at the people like us and materials really like us. I mean the objects like us that have the scale of classical scales may not be able to do time travel very easily or at all. But microscopic levels, we might actually have time travel quite intrinsic in particle physics. And we even get Hawking radiation as part of that, because black holes actually emit stuff sometimes as part of quantum mechanics and quantum fluctuations. That's how they have temperatures. That's how they can do Hawking radiation, black hole radiation, black body radiation. But radiation generally means that you're emitting something, and if you're not emitting anything, which is classically thought of for black holes, because even light cannot escape a black hole from within its event horizon. But turns out in quantum mechanics, black holes can actually sometimes sort of emit things, which is how they get a temperature. So this mixing of quantum mechanics with classical physics in the case of black holes, to describe them more fully, is what Stephen Hawking is credited for. So if you want more detail on this, you should definitely go back in our live streams in the past and look up all the different black hole type of lives that we have done. So time travel, in other words, all of that is to say that time, can we get 10 likes, by the way? Hi, Completely Insane. Hello, how are you? Hi, Clint. Hello, Doro. Hello, Insane. Hello, Clint again. Are you the daughter of Einstein because you're smart like him? Oh, thank you. He did have a daughter, I believe. But I think he had mainly, I can't remember. I think he did have a daughter, actually. Watches tumbleweed roll by. Completely Insane. How do you know Reese? I thought you were new to the channel, but thank you so much for the 10 likes, by the way, guys. Can we get 20 likes? So you know Reese? Can you say hi to my friend Hugh Janus? Hi, Hugh. Acacio. Hello. Steven, hello. Daughter of Einstein. That's a very big compliment. Thank you. Can you say hi to my friend Hugh? Hello, Hugh. I'm looking at it again. I'm number 8. Oh, thank you, Spore. My friend Spore, hello. Ray is the man, too quiet. Who knows me? Wonder Boy is here. She did it, Lo. What? What did I do? Reese is here. Okay, now that Reese is here, these people are going to be very busy talking about Titanics and ships and stuff. But I'll keep going with my physics spiels because I enjoy that and they enjoy Titanic. Don't do it. Do what? Do what? I'm not following this chat anymore. It's gone nuts already. Reese and is dumb new name. What? Have a lovely day. Hello, Atheo. Hi, Atheo789. Okay, guys, I want to be able to say hi to all the new people. And if you see any new people, can you say hi so that if I miss that they know that they're most welcomed here? Be nice to the new people. What? What is going on? Be nice to the new people. Welcome everybody. I'll keep going. So anyway, all of that was to say that time travel is not only allowed in physics, it is quite real actually for microscopic things. For example, particle-antiparticle pairs around a black hole. That's actually how we get black holes having temperature. So now, you're seeing sort of a mixing of the classical theories with quantum mechanics in the case of getting black holes to have a temperature and do Hawking radiation, which is really cool. But historically speaking, classical theories and general relativity, for example, and quantum mechanics have not got along. So there are the 4 fundamental forces of nature, if you remember. Number 1 is gravitation. It's very all-pervasive. It's an always attractive force, making it quite unique, actually, quite unique. And of course, you know what gravitation is. At least everybody has some intuitive feeling and some experiences with gravitation. For example, you might fall on your on the ground. You might hopefully not fall too far, but that is you experiencing gravitation. It is historically been explained with and described with Newtonian mechanics. Newton is the guy who gave us the mathematics and the physics to understand gravitation at that level. But then it was updated later on by Einstein. Okay, then number 2. So number 1 was the fundamental force was the gravitation. Number 2 is electromagnetism, the E&M forces, the force that leads to, charges repelling each other or attracting each other. So this is the type of force that is sometimes attractive and sometimes repulsive. If you have 2 like charges, they will repel each other. If you have opposite charges, they will attract each other. So not always attractive and not always repulsive. So this is the E&M force. It is quite a bit stronger than the force of gravitation, but it is also kind of all pervasive, as in we experience both gravitation and E&M quite a lot, quite universally. So as human beings, as intelligent beings, sort of intelligent beings on Earth here, we do know about gravitation and E&M quite a bit. We experience these forces. Then there's the 2 other forces that are also fundamental forces of nature that we don't experience that much, but that are also real. So these are the strong nuclear force and the weak nuclear force. These are fundamental forces that affect things that are more small and more at the quantum level and more at the subatomic level. For example, strong nuclear force is, of course, the force between quarks inside an atom, inside the nucleus, inside protons and neutrons. Protons and neutrons are subatomic particles that people thought a while ago in the 20th century were the sort of fundamental units of matter, but turns out that they further break down into quarks. So those types of things interact through this thing called the strong nuclear force. This is this 3rd fundamental force. Then there's also the weak nuclear force, and it turns out something like neutrinos will interact through that. So there's just all kinds of things going on. Particle physics has a large family of particles. But as far as the fundamental forces go, we've got the 4. Now, I'm kind of giving you the rehash of this before we start reading because this is going to come up. And it's basically good to get a summary now so that when we're in the weeds of it, it doesn't feel like, you're sentence by sentence learning this or hearing this. It's sort of like you're getting the big spiel first. So these four fundamental forces, gravitation, E&M, electromagnetism, that is strong nuclear force and weak nuclear force. The problem is, the issue is that there is nothing quite unifying all four yet. So as you probably can imagine, the three, E&M, strong nuclear force, and weak nuclear force, these are sort of kind of unified depending on the energy regimes that you're looking at. People have attempted sort of a unification of these three forces and have even succeeded to some extent and have probably been too happy about it, because unifying those three, there is still some hope. But really where grand unification is lacking is unifying these three with gravitation and sort of bringing together gravitation and what that means along with these other forces of nature, and finding the particle nature of gravitation, if there is one, and overall sort of those discrepancies between general relativity and quantum mechanics, these two different realms of physics, these two different scales of physics, not really seeing eye to eye and having these sort of internal issues between them, sort of like a marriage. Well, not a marriage, actually, the opposite of a marriage, sort of like two quarreling sides of physics that we want to marry together because we would like for them to have a unification so that we can rest easy that everything makes sense in a more consistent way. But there are two quarreling parts of physics that currently do not have a unification. And people have tried and failed, and Einstein tried. This was what he died trying. He wanted to have a more unified grand unification theory, is what he called it, GUT, grand unified theory, which would subsume and marry all these parts of physics together, and everything would fall under that more general theory. So a theory that's even more general than general relativity, for example, because remember, GR doesn't really give us anything about quantum mechanics and the particles that we keep discovering, right? So it's sort of this issue. There's an issue like where if general relativity does not do a good job or any job of saying anything about the particles that we experience and have discovered, then it's sort of lacking in that field, if you will. And quantum mechanics has certain bizarrenesses that are not explained in general relativity, and that too is sort of the complaint of a lot of these classical physicists. So both sides have issues with the other side, and they are, like I said, two quarreling partners, two quarreling parts of physics. So I wanted to tell you all about this because this is what we're about to launch into with this chapter called Unification from A Brief History of Time by Stephen Hawking. And he's going to take us through what we have kind of gone through already in the past, where we have talked about unification a few times at least, because this is it. This is what we're trying to do. We're trying to find a unified theory of everything, a unified theory of physics that will subsume everything underneath it, but it's incredibly difficult. And it's very challenging for any one person or even a body of people to kind of come up with it. And when people go ahead and try such a thing, they probably come up with sort of candidates of unification, if you will. And it's kind of like maybe not it could be that the candidate is just not good enough, and so it's not written about as much and not published about as much or not spoken about as much. Or it could be that it's sort of okay, but it's still not quite there yet. For example, I mentioned that there are theories that sort of unify E&M and strong nuclear force and weak nuclear force, but they still fall short because they don't unify those three with gravitation. So it's still not really, you can't really call it a grand unification theory if you don't quite, if you leave out something like gravitation. I don't know what you're saying, but I'm going to continue with my spiel because it's too much fun. But thank you, Reese, for being here. You've been missing every live. I see people are having fun with catching up with each other. So keep on keeping on, guys. So that's the standard as well, is that if you're going to call something a grand unification theory, you have to be able to explain gravitation. If you come from a particle standpoint and you sort of ignore gravitation, that's not going to make people very happy, because gravitation is, of course, something that we all experience. We would like to have an explanation of that without begging, that is. So so that's what's going on with the challenges of unification. Let me remind you that this is a sort of unfinished business. Einstein worked on it during his lifetime, towards the, till the very end, and did not succeed. But also, I will say that when Einstein was around, a lot of the facts of science were still not known. Obviously, we've evolved a lot, we've learned a lot more. Particle physics has come a very long way since that time. And so with all these other extra facts, he might have been able to come up with something. And basically, as far as I understand, string theory, superstring theory, is the candidate for grand unification theory at this point. And unfortunatamente, it is not testable because it has a lot of dimensions. And so that's sort of where we are. So I've kind of given you the, what's the word for, the spoiler alert of this story already. We will take a look at what Stephen Hawking says in this book. But from my own understanding of this whole topic on grand unification theory, I've kind of given you the spoiler already, the summary already, which is that pretty much it's very difficult. Most people can't really do the math and do it. They have found some things that are summarizing three of the fundamental forces, three of the four fundamental forces, but it's very difficult to also explain gravitation. And right now, probably the best candidate for a GUT is superstring theory, okay? And we will see what Stephen Hawking says about that. If we were reading a book by a string theorist, of course, they would say very strong words on that, I'm sure. And so we also have not brief history of time, that's this. We also have Brian Greene's book, The Elegant Universe, that we've also been covering stuff from. Are you going to pay for the honey wine? Can we get a super chat? Then we'll bring back the honey wine. Otherwise, we will just read books that are free from the library. She stole that arm wrestling guy's beer and got all slacky. Which arm wrestling guy? Which arm wrestling guy? What are you talking about? Scientists are not rich. I don't know what you're talking about. You have me mistook for Bill Gates or something. All particles are ready to defend the flow of the universe's perfection and destruction of living systems with each other. Okay. Hello, XXX. Has she done any more honey wine drunken lives? I did one honey wine live. And that was it. I'm not going to go get honey wine all the time, guys. I have a budget to stick to and a schedule of things to do here. So without the mighty Reese, the wildness has died down. It is true. Also, where have you even been, Reese? You don't even come to the lives. The honey wine live was when we found out more information about you guys that were quite terrifying pieces of information, actually. It's funny when she's pissed up? What does that even mean? You mean pissed off? Do you even know English? I like to say that to the British guy. When I can, I will upload a chapter at a time. Even Rose got drunk. Okay, you guys are saying too much stuff. I can't keep up. I will, however, donate my autism. Thank you so much for liking. Oh my God, did someone do a super chat? Steven! Aww. I was still reading these, these people's chats that are... Oh, not me. Have a good night, honey, says Combat Sports. See, Combat Sports is talking to the Honey Wine. Honey Wine, good night. Good night, Combat Sports. Spore says, hey, I'm following gravitation is key to explaining unification. Yes, thank you. Thank you, somebody's listening. Although I still think explaining unification is a terrible idea, but it's a fun idea. What do you mean explaining unification is a terrible idea? Why? Do you mean like here on the live or in general, like working on it? Do not get my attention with Titanic. I'm so done. I saw one of her shorts where she almost electrocuted herself in the basement. That's not the basement. That's my portable laundry machine. Upstairs. You're getting it all mixed up, Reese. Pissed up means drunk. How could you? Andrew does not respect the British. I do not. Not when it's Reese. And most others. Because you're a bad man? Clint was timed out? Why'd you try? Don't time out Clint unless he's said bad things. Sounds a bit melty. Brits do have a tendency to colonize stuff. Exactly. There. Spore can answer you guys. Okay. I don't know why you timed out Clint. Don't you dare. I've got the one guy who's listening and the other guy, Spore, that's listening. Don't you be timing out them. You're just happy that Reese is here. You guys, you should get married. Reese, do you want to be a US citizen? Gosh. My mods are extremely naughty, guys. Extreme naughtiness happens here because of the mods. Oh my God. Okay, you know what? Whatever. All right, we're going to talk about unification again. We're going to talk about unification. I already gave you the summary. Just keep your eyes and ears open now for the reading. Thank you so much, Stephen. Thank you so much, Stephen, for your massive support. Love you so much. And yes, I did read. I saw somewhere because you guys are, your comments are passing by. But I did read Stephen's book already. And so if he uploads a full chapter, then I'll take some time out to read the full chapter. Americans can say bad things too. Well, I think this one American and this other Belgian/Brit should just get together. Look at them being so naughty in my chat. Okay. All right. Unification of physics. So this is the chapter name here, the unification of physics. I already gave you the summary of what to kind of expect. Remember, we're going to want to unify gravitation, electromagnetism, strong nuclear force, and weak nuclear force. If somebody cannot, if somebody cannot if somebody cannot explain all four things, you can't really call it a grand unification theory. Okay? So we will see what happens with that and what Stephen Hawking says about this. As was explained in the first chapter, it would be very difficult to construct a complete unified theory of everything in the universe all at one go. So turns out this is quite difficult. Einstein struggled with this. A lot of people have struggled with this already. And by the way, superstring theory came out about 50 to 60 years after Einstein's death, I believe. So, you know, and so other than the subtle fact that you can't really test the theory because of its many, many dimensions, it is considered to be the best candidate. So I'll just give you the spoiler alert now. Expect some string theory in this chapter, okay? Do not time him out. Everybody behave. I want to be able to focus on the chapter. I don't want to see any bad things happening. Okay. So expect some string theory here going forward, okay? Thank you so much once again, everybody, for being here. Thank you to all the new people. And can we get more super chats? And Stephen, thank you so much. So instead, we have made progress by finding partial theories that describe a limited range of happenings and by neglecting other effects or approximating them by certain numbers. So this is what I kind of meant. The partial, I'm listening, but I'm almost asleep. Okay, you can just keep playing it in the background. Nathan, do not stop playing it. Keep it on. Keep it on and playing in the background. Just keep on going. Fall asleep to it. You can turn the volume down if I'm screaming too loud for you. So this is what I was mentioning earlier. When you unify three of the four forces, then that's a partial unification, and we cannot really call that a full-on unification. So there might be certain confusions if somebody claims to have a unified theory and they don't actually. Okay? Yeah, James does not come to the lives anymore. Like, I can't believe you still remember him. So instead, we have made progress by finding partial theories that describe a limited range of happenings and by neglecting other effects or approximating them by certain numbers. Chemistry, for example, allows us to calculate the interactions of atoms without knowing the internal structure of an atom's nucleus. Ultimately, however, one would hope to find a complete, consistent, unified theory that would include all these partial theories as approximations. So it's sort of like, okay, maybe we will have a bunch of partial theories and maybe they will help us to inch forward, if you will. Hello, Lover Toy Pops. Thank you, honey. Thank you. Thank you for the hearts. Ultimately, however, one would hope to find a complete, consistent, unified theory that would include all these partial theories as approximations and that did not need to be adjusted to fit the facts by picking the values of certain arbitrary numbers in the theory. The quest for such a theory is known as the unification of physics. Thank you so much for liking the live. Can we get 20 likes? Einstein spent most of his later years unsuccessfully searching for a unified theory. That's what I mentioned, which is that it's really sad that he didn't quite get to a successful unified theory and he died without one. Oh, my poor baby. But the time was not ripe. There were partial theories of gravity and the electromagnetic force, but very little was known about the nuclear forces. So remember I mentioned the two forces we knew so much about already, and it's all pervasive and it's very universally known and felt. If you've ever been shocked, and I mean electronically shocked, then then you know the electromagnetic force. If you ever fall to the floor, to the ground, then you know gravitation. But the strong nuclear force and the weak nuclear force we know a lot less about. Okay? We know now But we didn't know, first of all, these things, in the back in Einstein's time so much. And also, we experience them less because they are not really things that happen so much at our scales, at the scales that we generally experience life. Okay? So, moreover, Einstein refused to believe in the reality of quantum mechanics, despite the important role he had played in its development. So, Einstein was one of actually the critiques um, of quantum mechanics. There were many bizarre, many things about it that he thought were quite bizarre, and he did not like. And but yeah, as I was saying earlier, he was one of the initial contributors to quantum mechanics, what we call the old quantum mechanics, because he contributed the dual nature of light, the wave particle dual nature of light. So the fact that light is also a quantum particle is Einstein's work, some of his work. And so in spite of his great contribution to quantum mechanics, he himself was not a big fan, actually, of quantum mechanics, okay? Yet it seems that the uncertainty principle is a fundamental feature of the universe we live in, and he did not like that. Many people, like I was mentioning, did not like the fact that uncertainty principle is a fact of life. It's a fact of nature. It's an intrinsic part of the way we understand nature and physics, unfortunately, for the people who don't like it, but it is the truth. It is the truth. A successful unified theory must necessarily incorporate this principle, okay? As I shall describe, the prospects for finding such a theory seem to be much better now because we know so much more about the universe. But we must beware of overconfidence. We have had false dawns before. At the beginning of this century, for example, it was thought... Stop bullying him. Unless he's having fun with it. Then go ahead. As I shall describe, the prospects for finding such a theory seem to be much better now because we know so much more about the universe. But we must beware of overconfidence. We've had false dawns before, as in falsely thinking that we have unified things when we actually have not. Okay? At the beginning of this century, for example, it was thought that everything could be explained in terms of the properties of continuous matter, such as elasticity and heat conduction. Oh. The discovery of atomic structure and the uncertainty principle put an emphatic end to that. Then again, in 1928, physicist and Nobel Prize winner Max Born told a group of visitors to Göttingen University, physics as we know it will be over in 6 months. Gosh, his confidence was based on the recent discovery by Dirac. I love Dirac. Love me some Dirac. Dirac, by the way, gave us the relativistic equations the relativistic Schrödinger equations of matter in quantum mechanics. Okay. So his confidence was based on the recent discovery by Dirac of the equation that governed the electron. So, we had the Schrödinger wave equation for the electron to kind of tell us the position versus time for an electron and how that was really like a wave equation and whatnot. And then Dirac solved those and incorporated relativity into that. Okay, so he gave us the relativistic version of these equations. Thank you so much for being here and for liking the live. Thank you. It was thought that a similar equation would govern the proton, which was the only other particle known at the time. Because remember, we didn't discover all of the other, all the particles at the same time. I think it was 1932 when we discovered the neutron. So we didn't even know the neutron at that time. So it was thought that a similar equation would govern the proton, which was the only other particle known at the time. And that would be the end of theoretical physics, people thought. People thought. However, the discovery of the neutron and of nuclear forces knocked that one on the head too. So it's almost like people thinking that they've got it, but they don't got it. People thinking, oh, we discovered this and this and this, and this means that, and we've got it. It's sort of that feeling, but they don't got it. So in as early as 1920s, 1930s, people might have been overconfidently thinking that they've got it, but they actually did not got it. Okay? However, the discovery of the neutron and of nuclear forces knocked that one on the head too. Having said this, I still believe there are grounds for cautious optimism that we may now be near the end of the search for the ultimate laws of nature. That's what Stephen Hawking is saying. I'm not sure, that I agree exactly, but sure. In previous chapters, I have described general relativity, the partial theory of gravity, and the partial theories that govern the weak, the strong, and the electromagnetic forces. The last three may be combined in so-called grand unified theories or GUTs, which are not very satisfactory because they do not include gravity and because they contain a number of quantities like the relative masses of different particles that cannot be predicted from the theory but have to be chosen to fit observations. The main difficulty in finding a theory that unifies gravity with the other forces is that general relativity is a classical theory. This is what I was saying earlier. The classical side of physics and the quantum side of physics know not how to merge in a peaceful, harmonious marriage. They are still fighting. On the other hand, the other partial theories depend on quantum mechanics in an essential way. A necessary first step, therefore, is to combine general relativity with the uncertainty principle. As we have seen, this can produce some remarkable consequences. Such as black holes not being black and the universe not having any singularities but being completely self-contained and without a boundary. The trouble is, as explained in chapter 7, that the uncertainty principle means that even empty space is filled with pairs of virtual particles and antiparticles. So we've also talked about virtual particles and antiparticles quite a bit, and they were involved, remember, in the time travel type of discussion. These pairs would have an infinite amount of energy, and therefore by Einstein's famous equation, E equals mc squared, they would have an infinite amount of mass. Oh wow. Their gravitational attraction would thus curve up the universe to infinitely small size. Rather similar, seemingly absurd infinities occur in the other partial theories. But in all these cases, the infinities can be cancelled out by a process called renormalization. This involves cancelling the infinities by introducing other infinities. Although this technique is rather dubious mathematically, it does seem to work in practice and has been used with these theories to make predictions that agree with observations to an extraordinary degree of accuracy. Renormalization, however, does have a serious drawback from the point of view of trying to find a complete theory, because it means that the actual values of the masses and the strengths of the forces cannot be predicted from the theory, but have to be chosen to fit the observations. And that's not such a good thing, because remember, if we want a theory to give us the quantum properties that we are aware of from quantum mechanics, and that quantum mechanics has both predicted as well as found experimentally, we would want our new grand unification theory to be kind of giving us those same things that we already know about. It's kind of like, you want the new bigger theory to subsume the already known theories and experiments and results. Right? We don't want to not have the things that we know already from our great new work. right? We cannot reinvent the wheel to the point where now we don't know what we know. You know what I mean? That's what's going on here. So in attempting to incorporate the uncertainty principle, so it's almost like people have the puzzle pieces and they need the new picture to contain all of it. And if it doesn't, it's almost like they're forcing a little bit to have, like, they know that uncertainty principle has to be part of the new theory, you know, like it's almost like a going backwards type of thing. So in attempting to incorporate the uncertainty principle into general relativity, one has only two quantities that can be adjusted: the strength of gravity and the value of the cosmological constant. Hi, Clint. But adjusting these is not sufficient to remove all the infinities. One therefore has a theory that seems to predict that certain quantities, such as the curvature of space-time, are really infinite, yet these quantities can be observed and measured to be perfectly finite. This problem in combining general relativity and the uncertainty principle, that's the thing, like general relativity and uncertainty principle are very much not combined. So there's a problem. Had been suspected for some time, but was finally confirmed by detailed calculations in 1972. So look at this, 1972 is much later. 4 years later, a possible solution called supergravity was suggested. The idea was to combine the spin 2 particle called the graviton, which carries the gravitational force, which by the way is, I believe, a hypothetical particle even now. I don't think we've really discovered it yet, with certain other particles of spin 3 halves, 1, 1/2, and 0. In a sense, all these particles could then be regarded as different aspects of the same superparticle, thus unifying the matter particles with spin 1/2 and 3/2 with the force-carrying particles of spin 0, 1, and 2. So remember, we've talked about spin as a fundamental property of particles in quantum mechanics, and how many of the particles had a spin of 1/2, but some of the boson, the force-carrying particles, or the bosons, had more like whole number spins, like 0, 1, 2, things like that. So now we're talking about this superparticle. The virtual particle-antiparticle pairs of spin 1/2 and 3/2 would have negative. What are you doing? Don't time him out. This is too much drama in the chat. I need my viewers. You're not helping. Oh my God. Okay. This would cause many of the possible infinities to cancel out, but it was suspected that some infinities might still remain. Chat is always your enemy. Oh, I don't know about that, but the mods are being very rambunctious. Reese, you're never here anymore, and when you are, you're causing problems. You've got Doro so excited. Both of you are timing people out for no reason. And we want to be welcoming to the new people. But you threatened him only 10,000 billion times. Stop it. No. Oh my God. I'm going to unmod you, Reese. testing my patience. You're testing my patience. Patience. I thought causing problems in here was my job. You're getting unmodded. I don't like to press too many buttons. Acacio, do you know, Acacio, can you tell me who has caused this, who has started this issue? I'm not gonna go back up and read all the chats to figure out who here is to blame for this nonsense. Okay. So this would cause many of the possible infinities to cancel out, but it was suspected that some infinities might still remain. Good. Alcacio is paying attention to the, to the material of interest. So anyway, however, the calculations required to find out whether or not there were any infinities left uncancelled were so long and difficult that no one was prepared to undertake them. Even with the computer, it was reckoned it would take at least 4 years, and the chances were very high that one would make at least one mistake, probably more. I blame TikTok? For what? For bringing toxic culture to the chats? I forgot about the overloading. Honestly, if you want to keep talking about the overloading, that would be more helpful than whatever the frick all this other stuff is. So even with the computer, it was reckoned it would take at least 4 years, and the chances were very high that one would make at least one mistake, probably more. So one would know one had the right answer only if someone else repeated the calculation and got the same answer, and that did not seem very likely. Okay? Despite these problems and the fact that the particles in the supergravity theory, so this is a supergravity theory, did not seem to match the observed particles, most scientists believe that supergravity was probably the right answer to the problem of the unification of physics. It seemed the best way of unifying gravity with the other forces. However, in 1984, there was a remarkable change of opinion. Remarkable. Can we get 20 likes? It's I don't straighten my hair. Don't spread misinformation. People think my hair is naturally beautiful. Touch wood. Okay, so in 1984, there was a remarkable change of opinion in favor of what are called string theories. In these theories, the basic objects, so 1984, remember, quite a bit after the first time, for example, general relativity came about. Hello, Chickpea. Hello, Ver. Can you please like the live? Can everybody please like the live? Can we get super chats? My nice mod is here. Chickpea, can you ask people to do super chats and be helpful? As you know, my historically significant mods are most unhelpful sometimes. And they're stirring up a lot of trouble. Hello, Giorgio. How are you? Steven has spoken. He wants you to be nice, Reese. And Reese, how's your baby? Become more responsible. Giorgio, hello. At least it's not me. I'm fine and you. I'm good. I'm being nice tonight, but I hate being nice. Aw. I was stirring up trouble. Scan. Chickpea break. Oh, you're talking about the baby now. I was like, what are you talking about? She's got the first scan booked. Oh, ultrasound. Good luck. Good luck, you guys. Now that you're becoming fathers and all, can you please behave? God! Hi, Giorgio. Be careful, the mods are here. They will make a lot of fun of you. I'm talking to my mods. The bad ones. Okay, so in 1984, there was a remarkable change of opinion in favor of what are called string theories. Okay? So, in these theories, the basic objects are not particles which occupy a single point of space, but things that have a length, but no other dimension. So you're going to really love this, Reese. Reese loves string theory. Like an infinitely thin piece of string. These strings may have ends, the so-called open strings, or they may be joined up with themselves in closed loops called closed strings. A particle occupies one point of space at each instant of time. Thus, its history can be represented by a line in space-time, the world line. A string, on the other hand, occupies a line in space at each moment of time. So its history in space-time is a two-dimensional surface called the world sheet. Any point on such a world sheet can be described by two numbers, one specifying the time and the other the position of the point on the string. The world sheet of an open string is a strip. Its edges represent the paths through space-time of the ends of the string. The world sheet of a closed string is a cylinder or tube. So I'll show you the pictures here in a bit. Two pieces of string can join together to form a single string. So these are the descriptions of the strings that we are talking about here. In the case of open strings, they simply join at the ends, while in the case of closed strings, it is like the two legs joining on a pair of trousers. So by the way, we looked at this last night. In string theories, what were previously thought of as particles are now pictured as waves traveling down the string, like waves on a vibrating kite string. I'm going to make Clint a mod next. The emission or absorption of one particle by another corresponds to the dividing or joining together of strings. For example, the gravitational force of the sun on the earth was pictured in particle theories as being caused by the emission of a graviton by a particle in the sun and its absorption by a particle in the earth. So, the gravitational force of the sun on the earth was pictured in particle theories as being caused by the emission of a graviton by a particle in the sun and its absorption by a particle in the earth. I'm so sorry, Clint. Most nights, Reese is not here anymore, and it's a lot calmer, and please do come back tomorrow. Don't be upset. Why don't you listen to the reading that I'm doing and just don't interact with the mods anymore. Ignore them. Maybe I'm falling for a trick. I don't know what's going on really. Because I can't read everything that's happening in this dramatic chat. Clint, try to stay out of the drama and just focus on the physics. That's true. Doro did say one nice thing to Clint. I saw. Because of you, which we're happy you're here, but because of you, everybody's so overjoyed and they've got their childhoods back and everybody's getting into trouble because of this Reese right here, which is this person. Reese is the GOAT. Yeah. People love him so much. And because they're seeing Reese after a long time, Clint, they're just very happy. Don't take it so personal. Listen to the physics. And in fact, why don't you put in the chat messages your questions about physics and string theory and gravitation and particle physics? And that would be very helpful to both you and me. And just ignore Doro and Wonder Boy. Let them have fun with each other. They're meeting after a long time. Thank you, Doro. I saw that you said one nice thing to him. After threatening him multiple times, God, this isn't just a bunch of boyish drama. There's too much drama in my chat because all of y'all are men. Everybody sit down and shut up. I cannot with these men having so much drama. I don't even understand how so much drama is possible in a live stream. Hello, Zebulon. Is gravity a force? Yes, it is one of the fundamental forces. See, somebody finally asked a physics question. Disappointments. Clint, you're also responding to them a lot. Further provoking more such drama. When the better thing might be just to listen to the live stream physics and not provoke them. And they're just doing a bit of the brash banter, you know. Hello, Completely Insane is saying you're doing good. Thank you so much everybody for being here. Thank you for liking the live. Can we get 20 likes? They're being bantery because they're meeting after a long time. Some of these people will become fathers, believe it or not. But they come to this live stream to kind of just vent and relax and chill and be responsibility free. Oh my God. Chickpea. You too? Okay, all right. Okay, string theory has a curious history. It was originally invented in the late 1960s in an attempt to find a theory to describe the strong force. Drama is not a force, but in this live chat, Oh, was it you? Oh my god, it's his birthday, guys. Was it you that I just wished happy birthday? Happy birthday to you. Happy birthday to you. Happy birthday, happy birthday. Clint, do you want to do a super chat on your birthday? Clint, we would really appreciate your support on the holy and harmonious day that is your birthday. Happy birthday to you. Oh, hi. Thank you, Steven. I just had chickpeas. Thank you for liking the live. Is there an infinite equation for physics and we live a finite lifespan? The equation's complexities could take an... Oh, that's a great take. That is an interesting perspective, XXX. Doro, maybe this is something you could help with? He's saying, aw, it's fine. Clint, on your holy birthday, feel free to do a super chat. Feel free. Feel free. Feel free. It will become holier. Okay, string theory has a curious history. It was originally invented in the late 1960s. My card isn't set up. What kind of excuse-moi is that? There's also PayPal in the link in my bio, as any critter would tell you. And you should make you should make your birthday even more holy by adding your card. Add it. I don't use PayPal, sadly. But you do have a card. You should add your card. Your 16-digit card number, go ahead and add it. We'll wait. We'll wait. We'll wait. We're about to. So, string theory has a curious history. It was originally invented in the late 1960s. I don't know if there is a specific person that we name here, but we'll get into some of this history right now. Who started the idea? Yes, of course. I mean, a lot of people still believe in string theory. Michio Kaku, Brian Greene, Stephen Hawking, even though he's passed away, I believe, at this point. A lot of people believe in it. Why not? Samir Mathur, my professor, back at school. What is so funny? In some cultures, spending money on your birthday is actually the norm. Doro, you wouldn't know that since you are uncultured. But spending money is part of the culture. It is. Happy birthday to you. Okay, don't distract me. String theory has a curious history. It was originally invented in the late 1960s in an attempt to find a theory to describe the strong force. The idea was that particles like the proton and the neutron could be regarded as waves on a string. The strong forces between the particles would correspond to pieces of string that went between other bits of string, as in a spider's web. For this theory to give the observed value of the strong force between particles, the strings had to be like rubber bands with a pull of about 10 tons. In 1974, Jules Scherk from Paris and John Schwartz, there are some people's names, from the California Institute of Technology, published a paper in which they showed that string theory could describe the gravitational force, but only if the tension in the string were much higher, about 1,000 million, lots of millions, one with 39 zeros after it, tons. The predictions of the string theory would be just the same as those of general relativity on normal length scales, but they would differ at very small distances, less than 1,000 million, lots of millions of a centimeter. That's a centimeter divided by 1 with 33 zeros after it. Their work did not receive much attention, however, because at just about that time, most people abandoned the original string theory of the strong force in favor of the theory based on quarks and gluons, which seemed to fit much better with observation. So it hasn't always been worked on nonstop and continuously. So Scherk, this guy Scherk, Jules Scherk from Paris, died in tragic circumstances. He suffered from diabetes and went into a coma when no one was around to give him an injection of insulin. Oh no! Now that's a little rude, Clint. That begging comment. I don't know if I like that. Interesting. Hello, Ravi Saini. Okay, birthday Janve, good. 6 namaste, I like 5. You like 5? 5 what? Ravi Saini, hi. Hello, Ravi. How are you doing? Even Ravi wants to say happy birthday to you, Clint. Become happy. Discard this negative attitude and become happy. Be happy and positive. Positive only, okay? So Shark died in tragic circumstances. He suffered from diabetes. So Schwartz was left alone. The other guy, Schwartz was left alone as almost the only supporter of string theory. So back in those days, there weren't a lot of people who worked on string theory. I made a workshop. I'd send you pics, but you refused my friend request on Facebook, so I withdrew it. I didn't refuse your friend request. I get too many friend requests, and I don't answer most of them. Clint says, continue, do not stop. Ayank. Hello, Ayank. 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 Thank you. Thank you. We will continue to continue. Thank you so much. Somebody has spoken in the right way. Thank you, Ayank. So this interest in string theory was kind of dying down, especially because one of those people died. Shirk died. The guy from Paris. In 1984, interest in strings suddenly revived, apparently for two reasons. So even though Shirk died, Schwarz was left alone as almost the only supporter of string theory, but now with much higher proposed value of the string tension. So he kept working on it and updating it. In 1984, interest in strings suddenly revived, apparently for two reasons. One was that people were not really making much progress towards showing that supergravity was finite, or that it could explain the kinds of particles that we observe. So this other theory, supergravity, it wasn't really doing that good. The other was the publication of a paper by John Schwarz, this guy who did not die, and Mike Green of Queen Mary College, London, that showed that string theory might be able to explain the existence of particles that have a built-in left-handedness, like some of the particles that we observe. Whatever the reasons, a large number of people soon began to work on string theory, and a new version was developed, the so-called heterotic string, which seemed as if it might be able to explain the types of particles that we observe. Microwave is actually a type of, it is actually a type of physics field. So don't misinform people, Reese. Okay, so string theories also led to infinities. But it is thought that they will all cancel out in versions like the heterotic string, though this is not yet known for certain. String theories, however, have a bigger problem. They seem to be consistent only if space-time has either 10 or 26 dimensions instead of the usual 4. At this point, I believe we think it's mainly just the 10 dimensions, maybe 11, depending on the iteration of string theory. Of course, extra space-time dimensions are a commonplace of science fiction. So this is what I was mentioning earlier, if you missed the beginning of the live, is that string theory is the main candidate for a grand unification theory. But the issue is that it has so many dimensions, and we only experience 4, including time, and the 3 spatial dimensions. So it's not really something we can test out easily. And so physics, generally considered an experimental science, is going to have a lot of hard time to fully accept a theory that is not testable experimentally. So just keep that in mind as you go through this go through this lesson. So this is A Brief History of Time by Stephen Hawking. This is the 10-year anniversary version from 1998. Hello, the bears. Hello, Ayank. Hello, everybody. Okay, so now extra space-time dimensions are a commonplace of science fiction. Indeed, they provide an ideal way of overcoming the normal restriction of general relativity that one cannot travel faster than light or back in time. The idea is to take a shortcut through the extra dimensions. So instead of traveling faster than the speed of light or going back in, I hit my foot, or going back in time, you can take a shortcut through extra dimensions because you have all these extra dimensions in string theory. One can picture this in the following way. Imagine that the space we live in has only 2 dimensions and is curved like the surface of an anchor, ring, or torus. I'll show you this torus. Actually looks like that. See, a torus. If you were on one side of the inside edge of the ring and you wanted to get to a point on the other side, you would have to go around the inner edge of the ring. However, if you were able to travel in the 3rd dimension, you could cut straight across. So once again, see how here's the torus, and you could stay on the torus and go around the so once again, if you were on the one side of the inside edge of the ring and you wanted to get to a point on the other side, you would have to go around the inner edge of the ring. However, if you were able to travel in the 3rd dimension, you could cut straight across. So it's almost like you could either use just the dimensions of this torus, or you could cut straight across if you could access that dimension. So just keep in mind that sometimes what we experience might not be the entire total truth. Even though I was stressing as in I was emphasizing that physics is an experimental science and we live in the 4 dimensions, we experience the 4 dimensions, and so anything more than that is not testable. But we can still imagine certain things like, okay, well, what if we actually experience lesser dimensions than there actually kind of are in nature? And sort of like this torus example is kind of helping you to picture this, where you could think that you are on that torus as far as your dimensions, but what if you could access another extra dimension with respect to the torus, and then you can cut straight across? Why don't we notice all these extra dimensions if they are really there? So one question, of course, that we have kind of looked at before as well, is that if there are such extra dimensions like what string theory kind of needs in order to exist, why don't we experience them? Why can't we cut across? Okay? Why do we only see 3 space dimensions and 1 time dimension? The suggestion is that the other dimensions are curved up. I actually really like this suggestion. It's very fuzzy. It's a very cute suggestion, so listen up. So, why do we see only 3 space dimensions and 1 time dimension? Why not the other ones? The suggestion is that the other dimensions are curved up into a space of a very small size, something like a millionth of an inch. So very tiny indeed. This is so small that we just don't notice it. We see only 1 time dimension and 3 space dimensions in which space-time is fairly flat. Yes, close your eyes, Clint, and just listen. So we see only 1 time dimension and 3 space dimensions because the other dimensions are curled up like a little baby into a space of very small size, something like a millionth of an inch. It is like the surface of a straw. If you look at it closely, you see it is 2-dimensional, a straw. The position of a point on the straw is described by 2 numbers: the length along the straw and the distance around the circular direction. But if you look at it from a distance, you don't see the thickness of the straw, and it looks 1-dimensional, right? You'd have to go really close to the straw in order to really see its circumference. If you go far away, you would just think it's 1-dimensional. So it is with space-time. So it is with space-time. So similar thing happens with space-time. On a very small scale, it is 10-dimensional. and highly curved. But on bigger scales, you don't see the curvature or the extra dimensions. So maybe we live on a, we do live on a bigger scale than that particular dimension. And so maybe on our hour scales, we just see the 4 dimensions. But on very, very much more tiny scales, there might be 10 dimensions. If this picture is correct, it spells bad news for would-be space travelers. The extra dimensions would be far too small. Time travel people, the extra dimensions would be far too small to allow a spaceship through. So it's not like you can easily, with your macroscopic scales, go utilize this. However, it raises another major problem. Why should some, and by the way, this is good that he brings up this issue, because we did ask the question last time, why don't we see more visitors from the future if time travel is indeed realistically possible? We know it's possible, but is it pragmatic? Is it realistic? Partly it could be string theory giving us the answer, well, that even if you did it, the scales involved are so small, it doesn't really help macroscopic objects to do time travel like us, like aliens or human beings that are sort of, or aliens, well, human beings are all our scale, but aliens might also be our scale, who knows? Or maybe aliens can actually access the 10 dimensions because maybe they're very tiny. Who knows? We have to keep an open mind when it comes to aliens as well, okay? So if this picture is correct, it spells bad news for would-be space travelers. The extra dimensions would be far too small to allow a spaceship through. However, that's the thing. Like, we are thinking about spaceships and our sizes, like classical sizes, but for all we know, things are happening at a much smaller scale, and it would not be a spaceship that's going to be visiting us from the future, right? It could be something very different. Okay, so okay, next is, it raised another major problem. There's another major problem. By the way, everybody, welcome to the chat, welcome to this live, and can you please like the live, and can we get 20 likes? Welcome, welcome, welcome. Can we get 20 likes, please? So there's another major problem. Why should some, but not all, of the dimensions be curled up into a small ball? So we talked about the little curly ball thing in which exists the extra dimensions that we don't experience as people. But why are only some of them curled up in a little ball like a sleeping baby or a kitten, but not all? Why some, but not all? Why did one time dimension and 3 space dimensions flatten out while the other dimensions remain tightly curled up? Oh, I love that sentence. One possible answer is the anthropic principle. 2 space dimensions do not seem to be enough to allow for the development of complicated beings like us. For example, 2-dimensional animals living on a 1-dimensional Earth would have to climb over each other in order to get past each other. If a 2-dimensional creature ate something, it could not digest completely. It would have to bring up the remains the same way it swallowed them. Oh gosh. Because if there were a passage right through its body, it would divide the creature into 2 separate halves. Our 2-dimensional being would fall apart. Similarly, it is difficult to see how there could be any circulation of the blood in a 2-dimensional creature. So this is sort of an anthropogenic, not quite anthropogenic, but anthropic principle. It's seeing things in terms of us, like we exist and we are complicated beings, and this universe hosts us complicated beings. And so it has evolved in a way where we experience the 3 spatial dimensions and the 1-time dimension. The 4 dimensions really make it possible for us to be as interesting and as complex. There would also be problems with more than 3 space dimensions. The gravitational force between two bodies would decrease more rapidly with distance than it does in 3 dimensions. True. Gravitation would be different. That's so interesting. In 3 dimensions, the gravitational force drops to 1/4 if one doubles the distance. In 4 dimensions, it would drop to 1/8. Oh my gosh. In 5 dimensions to 1/16 and so on. Nice to see you. The significance of this thing of the gravitation force being falling off is the significance of this is that the orbits of planets like the Earth around the Sun would be unstable. The least disturbance from a circular orbit, such as would be caused by the gravitational attraction of other planets, would result in the Earth spiraling away from or into the Sun. So if you mess with gravitation, even though people who are not unifying gravitation enough with the rest of the stuff might be happy to ignore gravitation, but actually you cannot ignore gravitation, right? So you don't want the Earth to not be stable like orbiting the Sun. All that instability, if you mess with gravitation, would also imply that we would never be here. We're here because the Earth is stable. We are here because the Sun is stable. We're here because there is a stable gravitational attraction between the Sun and the Earth. So, again, we are part of a universe and a world where we exist, where we can be. So, we would either freeze or be burned up. If we were any closer to the Sun or any farther away because of gravitation being messed up, because of those dimensions, the extra dimensions, if we experienced them, gravitation would be different. In fact, the same behavior of gravity with distance in more than 3 space dimensions means that the Sun would not be able to exist in a stable state with pressure balancing gravity. It would either fall apart or it would collapse to form a black hole. In either case, it would not be of much use as a source of heat and light for life on Earth. On a smaller scale, the electrical forces that cause the electrons to orbit around the nucleus in an atom would behave in the same way as gravitational forces. Thus, the electrons would either escape from the atom altogether or would spiral into the nucleus. In either case, one could not have atoms as we know them. So this whole dimension thing, remember, we live in a very finely balanced universe. So when you mess up the dimensions that we experience, the ones that are curled up into a ball versus not, the ones that are not curled up into a ball of extreme small size, are the ones that we experience, the 3 spatial dimensions and the 1 time dimension. And those dimensions that we do experience really rule everything, such as gravitation, electromagnetism, and the sort of the scales of these forces as well. If you mess up gravitation or electrons and in an atom, for example, then you would not, again, our world would not be the same. We would not be the same. We would not be probably here because it would not be a habitable or hospitable environment that would make complex organisms like us. If we had all, dove into the Sun because the gravitation is messed up, then, or been too far from the Sun, it would not have made us. Okay, we would not be here. And if electrons, if we are made of ordinary matter, made up of atoms. So if stable atoms were not a thing, again, we would not be here. So these are the things, it's almost like it's perfectly set up for us. Could we find these extra dimensions with an electron microscope? They're quite small. I'm not sure that they're big enough for the electron microscope, actually. Let me tell you again, this is the size of a millionth of an inch. So you can look it up as to whether you can see them through an electron microscope. I think that is quite small. That's not electron microscope levels, okay? So all this stuff spiraling in and out, not being stable, would not help our evolution at all. It seems clear then that life as we know it, it becomes a philosophical sort of, takes a philosophical turn almost at this point, right? It seems clear then that life as we know it Hello everybody, thank you so much for being here. Can we get 20 likes? Life as we know it can exist only in regions of space-time in which one time dimension and 3 space dimensions are not curled up small. This would mean that one could appeal to the weak anthropic principle, provided one could show that string theory does at least allow there to be such regions of the universe, and it seems that indeed string theory does. There may well be other regions of the universe or other universes, whatever that may mean, as in other universes, that is, or other parts of this universe, sure, in which all the dimensions are curled up small, or in which more than 4 dimensions are nearly flat, but there would be no intelligent beings in such regions to observe the different number of effective dimensions. So you could have the uncurledness of those extra dimensions and be like, yeah, sure, string theory, please allow some parts of the universe or some other universes to have the extra dimensions be more of a thing. You could, but those parts of the universe or other universes would not have us in them, okay? Because the universe in which those extra dimensions are not curled up would be inhospitable for life. So okay, so it seems clear that then that life as we know it can exist only in regions of space-time in which one time dimension and 3 space dimensions are not curled up small. This would mean that one could appeal to the weak anthropic principle, provided one could show that string theory does at least allow there to be such regions of the universe, and it seems that string theory indeed does. So there may very well be other regions of the universe or completely other universes where the dimensions are curled up, in which all the dimensions are curled up small, or in which more than 4 dimensions. So it's basically, it's not so specific. It doesn't have to be so specific. Maybe there could be a universe in which more dimensions are like the ones that we experience, or there could be dimensions that are curled up, more ones that are curled up. It's just that we would not be parts of that universe. Another problem is that there are at least 4 different string theories. So, gosh, this is quite complicated. So, string theory, there's different types apparently. Open strings and 3 different closed string theories. So, the other thing is that the string theory community, I mean, it's smaller than some of the other communities that at least I know of. But I'm sure even within that community, there is quite a bit of diversity and different people kind of trying out different things. So let's look at this. Open strings and 3 different closed string theories, and millions of ways in which the extra dimensions predicted by string theory could be curled up. Why should just one string theory and one kind of curling up be picked out? Right? For a time, there seemed no answer and progress got bogged down. Then from about, give me 1 second. I have to check on Sachi. Sachi, mama. Oh, okay, she's fine. I thought she was down here. I thought she came down here. They're not here right now. I think they're upstairs. Thank you. It's from Wayfair. Yeah, they're not here right now, but I think they'll come down once their snack. Yeah, they'll come down once the snack is falling. Thank you, Clinton, Zebulon, and everybody. Thank you, Chickpea. Thank you, Doro. So another thing is, why should just one string theory and one kind of curling up be picked out? For a time there seemed no answer and progress got bogged down. Then from about 1994, people started discovering what are called dualities. Different string theories and different ways of curling up the extra dimensions could lead to the same results in 4 dimensions. Moreover, as well as particles, which occupy a single point of space, and strings, which are lines, there were found to be other objects called p-branes. So that's the letter P with the branes, B-R-A-N-E-S, which occupied 2-dimensional or higher dimensional volumes in space. Actually, I'm kind of remembering this from my GR class, actually. I think he did talk about branes. Brain as in B-R-A-N-E-S. So, so the p-branes occupied 2-dimensional or higher dimensional volumes in space. A particle can be regarded as a 0 brane and a string as a 1 brane, but there were also p-branes for p equals to 2 to p equals to 9. Good night, Doro. Yeah, so, well, there's the, depending on which type of thing, you're either a 0 brane, a 1 brane, but basically p-branes meaning p number of branes, B-R-A-N-E-S. Okay, so let's see. What this seems to indicate is that there is a sort of democracy among supergravity, string, and p-brane theories. They seem to fit together, but none can be said to be more fundamental than the others. They appear to be different approximations to some fundamental theory that are valid in different situations. People have searched for this underlying theory, but without any success so far. However, I believe there may not be any single formulation of the fundamental theory any more than, as Gödel showed, one could formulate arithmetic in terms of a single set of axioms. Instead, it may be like maps. You can't use a single map to describe the surface of the Earth or an anchor ring. You need at least 2 maps in the case of the Earth and 4 for the anchor ring to cover every point. Right? Huh. Ha 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 ha. Each map is valid only in a limited region, but different maps will have a region of overlap. The collection of maps provides a complete description of the surface. Similarly, in physics, it may be necessary to use different formulations in different situations. So don't expect the same type of brains to work all the time. But 2 different formulations would agree in situations where they both can be applied. The whole collection of different formulations could be regarded as a complete unified theory, though one could not be expressed in terms of a single set of postulates, right? You know, but can there really be such a unified theory, or are we perhaps just chasing a mirage? There seem to be 3 possibilities. So it seems like the brain stuff is basically saying, like, it's not like the same type of string theory will always work. Right? Not the same. But are we chasing a mirage? What's really going on here? So the three possibilities are: number one, there really is a complete unified theory or a collection of overlapping formulations, which we will someday discover if we're smart enough. So it could be that it's so complicated that we just haven't been able to get to it yet, and it's still a research topic. And I do believe that that is generally still kind of regarded. Like, if you work on a grand unification theory, it is still novel. It is still considered to be not really something that we totally understand or get yet. Number two, there is no ultimate theory of the universe, just an infinite sequence of theories that describe the universe more and more accurately. So it could be that we cannot actually unify all these theories, and quantum mechanics works for quantum and classical works for classical. You know, maybe there is not a way to really unify them. And we have to accept that certain theories work in certain circumstances for certain scales, and that's about it, in certain regimes, and that's about it. And we can't really have a full-on unification. Number three, there is no theory of the universe. Events cannot be predicted beyond a certain extent, but occur in a random and arbitrary manner. That's the number three, which is a little, I mean, it's a little pessimistic, but that's basically saying that even though we have all these theories, we have all these things that can explain things, but that is not the end all be all. Things are just kind of happening in the universe, and sometimes they can be explained and sometimes they cannot be explained. And just randomness and sort of arbitrary things happening is just a part of life. That's the number three option. Disingenuous. Some would argue for the third possibility on the grounds that if there were a complete set of laws, that would infringe God's freedom to change his mind and intervene in the world. So there could be sort of like a spiritual or religious reason preventing us from having a theory of everything, because that prevents the Almighty from doing things that God might want to do at some point, if you believe in a God. So it's a bit like the old paradox: can God make a stone so heavy that he can't lift it? But the idea that God might want to change his mind is an example of the fallacy pointed out by Saint Augustine of imagining God as a being existing in time. Time is a property only of the universe that God created. Presumably, he knew what he intended when he set it up. So, okay, leave him alone. Enough fighting. Just leave it alone, everybody. Chickpea, Clint, stand off. Stand off and don't fight. Just listen to this. So, with the advent of quantum mechanics, we have come to recognize that events cannot be predicted with complete accuracy. So that's just accepted in quantum mechanics. If you had an issue with that, it has to end with quantum mechanics saying that, I'm so sorry, not everything can actually be said with total certainty always. Okay, meh to what, Zebulon? So, if one likes, one could ascribe this randomness to the intervention of God, but it would be a very strange kind of intervention. Not that we tell God what to do, but the types of intervention that, you know. Oh, wow, I just looked at the moon. Ah, the moon is getting bigger. It's a waxing gibbous right there. I looked, I turned and I looked directly at the moon. Goodness, wow. So, if one likes, one could ascribe this randomness to the intervention of God, but it would be a very strange kind of intervention. There's no evidence that it is directed toward any purpose. Indeed, if it were, it would by definition not be random. In modern times, we have effectively removed the third possibility above by redefining the goal of science. Our aim is to formulate a set of laws that enables us to predict events only up to the limit set by the uncertainty principle. So there's sort of a limit up to which we can predict things. After that, the uncertainty principle kind of takes over and says that you can't predict things beyond this, to an accuracy beyond this. The second possibility that there is an infinite sequence of more and more refined theories is in agreement with all our experience so far. On many occasions, we have increased the sensitivity of our measurements or made a new class of observations, only to discover new phenomena that were not predicted by the existing theory, and to account for these, we have had to develop a more advanced theory. It would therefore not be very surprising if the present generation of grand unified theories was wrong in claiming. Oh, 1 second. I need to put this down. Sachi! Okay. Sachi, mama. Sachi! Come, Sachi. Okay. Fuji, why don't you eat from this side? Okay. I have to manage. Oh, poor Baji. Here's Baji, by the way. Baji, say hi. Baji, say hi. So the second possibility that there is an infinite sequence of more and more refined theories is in agreement with all our experience so far. On many occasions, we have increased the sensitivity of our measurements or made a new class of observations. Don't fight, boys. I'm talking to the kitty cats, but it applies to you as well. Hey, hi, Sachi Mama. Kejo Shona? Come, baby. Hee hee hee. Baji belly, huh? Sachi. Let me see if Sachi will come to lap. Okay, okay. Go play. Okay, so this notion that perhaps we're just kind of getting more and more accurate with our different theories, more and more sensitive to various things, that could be a thing too. So on many occasions, we've increased the sensitivity of our measurements or made a new class of observations only to discover new phenomena that were not predicted by the existing theory. And to account for these, we've had to develop a more advanced theory. It would therefore not be very surprising if the present generation of grand unified theories was wrong in claiming that nothing essentially new will happen between the electroweak unification energy of about 100 GeV and the grand unification energy of about 1,000 million GeV. 1,000 million. We might indeed expect to find several new layers of structure more basic. Oh gosh, we might indeed expect to find several new layers of structure more basic than the quarks and electrons that we now regard as elementary particles. Goodness. It would not be very surprising. So it's basically like saying that we've got these different theories, but they just manifest at different sensitivities. Certain certain sensitivities are found at a certain energy scale, and others are found as you change that scale. Let's read this again. It's a very interesting statement. Happy birthday, Clint. Don't, just leave it alone. Let him have a good birthday. Hello, Ben. No, I'm a very early person. It is early in the morning now, isn't it? So, it would therefore not be very surprising if the present generation of grand unified theories was wrong in claiming that nothing essentially new will happen. So it's basically saying that if we say that nothing will happen that's new between a certain energy and a certain other energy, but then we increase our sensitivity between those energy scales, like it's simply a matter of increasing our sensitivity where we can measure with even better accuracy or have better instruments, etc. And it's almost like we are discovering realities that kind of just provide a correction to what we already knew. It's almost like we discovered protons and we thought that they were the elementary particle, but turns out that they are made of quarks. So quarks is like another layer deep, another level down from the protons, right? That's sort of discoveries. Maybe that's just a fact of life. Maybe it's a fact of life that we keep on discovering things at various sensitivities, and it's that's just how things are. It's a number of theories that explain the full universe, not just one theory. And the number of different theories are not wrong or anything. They're just existing at various different sensitivities. However, it seems that gravity may provide a limit to this sequence of boxes within boxes. As I kind of mentioned in my spiel before, in this summary, all this stuff about the sensitivities and whatnot, it's all good, but the problem is gravitation being such a universally experienced force, and then not being explained by particle physics is sort of this embarrassment. You know what I mean? It's turtles all the way down. So if one had a particle with an energy above what is called the Planck energy, 10 million GeV. So that's 1 followed by 19 zeros. Its mass would be so concentrated that it would cut itself off from the rest of the universe and form a little black hole. Thus, it does seem that the sequence of more and more refined theories should have some limit as we go to higher and higher energies, so that there should be some ultimate theory of the universe. Should be. Of course, the Planck energy is a very long way from the energies of around 100 GeV, which are the most that we can produce in the laboratory at the present time. Actually, no, we can now, so this book is a little old. This book was written, it was updated in 1998, it looks like. Now we can attain things like center of momentum energy of around 14 TeV at the Large Hadron Collider. Okay, so we can attain higher energies than 100 GeV at this point. So the Planck energy would be a long way from those energies, even 14 TeV, right? Which are the most that we can produce in the laboratory. We shall not bridge that gap with particle accelerators in the foreseeable future, the Planck energy, that is. The very early stages of the universe, however, are an arena where such energies must have occurred. I think that there is a good chance that the study of the early universe and the requirements of mathematical consistency will lead us to a complete unified theory within the lifetime of some of us who are around today, also presuming we don't blow ourselves up first. What would it mean if we actually did discover the ultimate theory of the universe? As was explained in chapter 1, we could never be quite sure that we had indeed found the correct theory, since theories can't be proved. So that's the thing. Oh, by the way, if you're joining, can you please like the live? Can we get 20 likes? That's the thing. Like, it's not like you can work on just a theory until it was sort of proved out. You can't really know that it's true. So, as was explained in chapter 1, we could never be quite sure that we had indeed found the correct theory, since theories can't be proved. One second. One second. Okay, let's keep going. So, so we wouldn't really know that the theory is correct until we experimentally proved it out. Thank you so much for liking the live. Can we get 20 likes? But if the theory was mathematically consistent and always gave predictions that agreed with observations, we could be reasonably confident that it was the right one, right? For example, general theory of relativity is pretty hard theory for a lot of people, but it has made a number of predictions that are experimentally proved out. They're correct. They've been measured. So that's why it's highly successful. It's considered to be a highly successful theory, even if it's not explaining anything and everything, but it is considered to be a highly successful theory because of its great experimental success. Okay? So the observations and the experimental success mean a lot. So anyway, if the theory was mathematically consistent and always gave predictions that agreed with observations, we could be reasonably confident if we had such a theory of everything, right? It would bring to an end a long and glorious chapter in the history of humanity's intellectual struggle to understand the universe, but it would also revolutionize the ordinary person's understanding of the laws that govern the universe. It really would. In Newton's time, it was possible for an educated person to have a grasp of the whole of human knowledge, at least in outline. But since then, the pace of the development of science has made this impossible. It is a lot more where did you go? Who? It is a lot more complicated nowadays. Particle physics, all of the details, it's very complicated. So, but since then, the pace of the development of science has made this impossible because theories are always being changed to account for new observations. They're never properly digested and or simplified so that ordinary people can understand them. You have to be a specialist, and even then, you can only hope to have a proper grasp of a small portion of the scientific theories. So this is a good point that Stephen Hawking is making here in his book, A Brief History of Time, which is that it used to be that we knew kind of a smaller amount of physics in the past, say during Newton's time, and you could kind of know everything that was known about physics in a nutshell more easily. Nowadays, there's just so much more complications, complexities. You would have to be a specialist to really understand a certain topic, and you would definitely probably not get around to understanding all of the different topics. But if you found a grand unification theory, sort of a theory of everything, you could maybe just learn that. Now, I think that we're learning here that would be very complicated in itself, but it might actually make something like there's some, we can at least wish for something a bit more digestible for people to kind of just digest that this is it. This is the all of human knowledge that I need to know about in physics, if they could digest the theory of everything, right? So only a few people can keep up with the rapidly advancing frontier of knowledge, and they have to devote their whole time to it and specialize in a small area. The rest of the population has little idea of the advances that are being made or the excitement that they're generating. 70 years ago, if Eddington is to be believed, only 2 people understood the general theory of relativity. Nowadays, tens of thousands of university graduates do, and many millions of people are at least familiar with the idea. If a complete unified theory was discovered, it would only be a matter of time before it was digested and simplified in the same way. And by the way, that's why we have this channel, is to understand these topics and spread this knowledge to more people so that it's not just the experts that know the topic who are working on it, but we can all know these topics, at least be able to kind of be well versed in them and know about them and be aware of them, right? Thank you so much, everybody. Thank you for liking the live. Feel free to do a super chat and feel free to stop fighting in the chat for no reason. If a complete unified theory was discovered, it would only be a matter of time before it was digested and simplified in the same way and taught in schools, at least in outline. We would then all be able to have some understanding of the laws that govern the universe and are responsible for our existence, right? Even if we do discover a complete unified theory, it would not mean that we would be able to predict events in general for 2 reasons. The first is the limitation that the uncertainty principle of quantum mechanics sets on our powers of prediction. We can't know things for sure because of quantum mechanics and uncertainty principle. Next is there is nothing we can, so there's nothing we can do about that. In practice, however, this first limitation is less restrictive than the second one. So the next thing is it arises from the fact that we could not solve the equations of the theory exactly except in very simple situations. We cannot even solve exactly for the motion of 3 bodies in Newton's theory of gravity, and the difficulty increases with the number of bodies and the complexity of the theory. We already know the laws that govern the behavior of matter under all but the most extreme conditions. In particular, we know the basic laws that underlie all of chemistry and biology, I guess. Yet, we have certainly not reduced these subjects to the status of solved problems. So it's kind of like saying, chemistry and biology are sort of built upon physics and math, right? But that doesn't mean that we've solved every problem that there is in chemistry and biology. I mean, right? The medical field, for example, has a lot of open questions still. That depends on biology and chemistry. Thank you so much. Thank you so much, Zebulon 181. What glues atoms together? What, atoms together, or do you mean what is happening right now? Clint, calm down. Thank you so much, Zebulon. Thank you so much. What glues atoms together? So the nucleons are glued together by the strong nuclear force, the gluons. Were you asking about that? So we already know the laws that govern the behavior of matter under all but the most extreme conditions. We're almost done with this chapter. In particular, we know the basic laws that underlie all of chemistry and biology. So in theory, in some way of speaking, we do understand the underlying principles of chemistry and biology, but do we have every answer to every question in chemistry and biology? No, because those fields are very complicated, and we're not gonna just know everything by knowing the fundamentals, right? The fundamentals only help us with some stuff, but more complications have to be still researched. So yet we have certainly not reduced these subjects to the status of solved problems. We have as yet had little success in predicting human behavior from mathematical equations. So, here we are talking about trying to understand the entire universe's physics and math and explanation, but there are things that are yet to be understood even about biology or psychology or medicine. And these are based upon more fundamental sciences that are understood, but still we don't understand a lot of things. Even the things that are based on understandable or understood fundamental principles can still have a lot of complications that are yet to be unearthed. So even if we do find a complete set of basic laws, there will still be in the years ahead the intellectually challenging task of developing better approximation methods so that we can make useful predictions of the probable outcomes in complicated and realistic situations. So it's not just about getting the mathematics done for the theory of everything. It is also about understanding what it really means for us in various different complicated and realistic situations. The underlying theory could be found or known or discovered or worked upon, and it would still not answer every question. So partly we might have attacked the problem from the other side, which is that maybe we've started to be aware of some more complications that we do sort of understand at a certain level, but there might be something underlying that we don't yet understand. But just by understanding the underlying would not necessarily privy us to the complications and the more specific cases. A complete, consistent, unified theory is only the first step. Our goal is a complete understanding of the events around us and of our own existence. Aww. So this was the chapter 11 from A Brief History of Time. It is called The Unification of Physics that we just talked about from A Brief History of Time by Stephen Hawking. That brings us to the next chapter, which is called Conclusion. So we are really towards the very end of the book, so we're almost quite done. We will do conclusions tomorrow. So we will do conclusions tomorrow, but that was a very interesting chapter indeed. I liked how he sort of ended with the theory of everything being not the end-all be-all, because I think people get caught up too much in the theory of everything being sort of the end-all be-all. Whereas actually, like he said, the underlying principle, even when that is known, can still actually leave a lot of questions unanswered for more realistic and specific situations, just like we see in chemistry, biology, medicine, psychology, all of that, right? Just because you know some fundamental principle doesn't mean that you've answered every question there is or solved every problem there is. But it is, of course, very fun to have a fundamental theory and fun to have a fundamental principle which kind of explains everything. But even then, I'm not sure that it would really truly explain everything, because it would still need work to be applied to all of the different relevant situations. So that's the theory of everything, referenced from Brief History of Time by Stephen Hawking. This was the discussion of today. There's a lot going on in the chat. If you're still here and if you're joining and you've missed the beginning of the live, then please do go to the left and rewind the show here. And if you're here and have any questions, then let me know. I'll hang out for a little bit, but then I will be going to bed. So let me know your questions, let me know your comments, and I do appreciate you being here very much. Can we get 20 likes? Can we get super chats? Welcome, thank you. We will see you again tomorrow. We will hang out for a little bit here now and make friends with everybody, and let me know if you have any questions, and eagerly awaiting any last thoughts or comments, okay? Thank you, everybody. Thank you, Clint. Thank you, Zebulon. Good night. Thank you, XXX. So tomorrow, join us again. We will talk about the conclusion of this book. It should be pretty interesting. It should be really interesting, because we'll bring together all of this stuff tomorrow, and it's not a very long chapter, and we also have little tidbits on various famous scientists, Albert Einstein, Galileo Galilei, and Newton, and that will be that book. Then we'll be done with this book and kind of talking about this book, and we will go back to Brian Greene's book, The Elegant Universe, and we will also try to bring back somebody's book request, Atom, by Dr. Krauss. We will work on that as well. But I wanted to get through this book because it has a number of very interesting topics, and written very simply by, of course, Stephen Hawking. Very famous book. So here we are. I am not addressing any more of the drama from tonight. If you have a physics question, please do let me know in the chat. And if you have otherwise positive things to say or do, then go ahead. And if you want to do a super chat, go ahead. If you want to like the live, go ahead. And I want to thank you all very much again for being here. Thank you so very much. Please do like the live. Can we get 20 likes? Thank you. And glad people stayed and enjoyed the discussion today. Thank you so much. Clint, I'm beginning to see why the mods have an issue with you. See, at first I was trying to protect your experience here, and I was hoping that you'll have a good one. But you've really refused to have a good day. Indeed. But certainly we will wish you a happy birthday and a good evening tonight. That equation means the energy mass equivalence that we get from special theory of relativity from Einstein. We got the relative nature of space-time and energy and mass equivalence from his special theory of relativity. You may want to Google it. We've talked about it a lot, by the way, in the past. So by the way, I want to plug that you, if you're new to the channel, you should go and check out, and feel free to check out all of the live stream episodes that are already posted in the past under the live tab of this channel to get caught up with everything that we've discussed. And special theory of relativity we've discussed in a lot of detail in the past, for sure. For sure. It might be a few months ago now, but you'll find it if you go back to the lives, okay? Go back in the lives from before. Hi, Shona. Fuji Baba is here. Thunder woke me up. I hop in. Is Clint still going on? He is. And he's really disappointed me with the drama levels. Ben says, has there ever been a cat? I don't know, but there's definitely a cat in my space now. Fuji? Oh my gosh, Fuji's eating my dinner. And licking his lips. Fuji? No, Fuji. No, Fuji. Are you drinking the chickpea water? We're all in space. Fuji's drinking the chickpea water. No, Fuji. And Baji. Look at the crowd here now. Everybody. Baji! I need to run the dishes. Some children are being very extra right now. Oh, you guys can look at, if you have any questions, keep them coming, and I'll let you look at the kitty cats here. There is Sachi Mama, right there. Oh, whoops, I didn't mean to do that. Here is Sachi. Yup. Here you go. You can look at Sachi if you want. She's working on something. She's working on something. Okay. Thank you for the super chats today, guys. Thank you so much. Really appreciate. As usual. Sachi is playing very vigorously. With extreme vigor, she's playing. Extreme vigor, indeed. Extreme vigor. Oh my gosh. Look at that. Look at that. Good night, Doro, and good night, Chickpea, and good night, Clint. Good night, everybody. Slash, you can stay if you want. Baji, can you please not eat the human food? Oh man. No, Sachi, you're too cute. Let me show you. Hi, Sachi, Mama. Hi. Oh, you're so cute. Oh, you're so very cute. You're such a cutie. You're so cute. Oh, you look at your face. Oh, you're so cute. Good job. Good job, everybody, today. Good job, everybody, for listening. Thank you so much. Everybody, have a good night. Thank you indeed for being here. See you tomorrow. See you tomorrow. Have a good night. Thank you. Thank you. Hello, Dark Gloom. How are you doing? So we just finished up a whole topic of discussion tonight on the unification theory of physics, or the theory of everything. We just finished that topic. It's been an interesting night indeed. So you should go back in the live and check out the full episode. Just rewind. Thank you, Dark Gloom. Thank you, Robin. Hello, Dark Gloom, and hello, Robin. I see Robin says, I see cat, I click. Good. You get cat here for sure. Dark Gloom says, hey now. Robin says, I see cat, I click. There you go. Here is cat. Oh. Oh. Oh, you're such a cute baby. Oh, you're such a cute baby. Mm-hmm. Oh, such a cutie. Kitty. Yes. I have to use the bathroom, guys, but here you go. Here's your kitty cat view. Try to zoom in a bit. You can see even better. I won't block your view. Wow, Suji. Suji is very active at this time. Go ahead, Suji. Go play. Play time for Suji Mama. Have fun, guys. Enjoy. I need to charge the phone. One last look at the kitty cats. We're gonna go to bed. Thank you, everyone. Here's the guy, here's the author that we were just reading.